This video is part of a series on straight line. It does involve statistics, but rather include it with statistics. Because it involves finding the equation of a straight line, I've included it with the straight line videos. This is a scatter diagram showing. A series of points have been plotted. PE marks against art marks. So someone has scored 2 in art but 8 in PE. We go to 2 on the horizontal for the art score, and we go vertically up 8 for the PE score, and that cross there is the point 2, 8. So we've plotted PE against art. Art's on the horizontal. The next point here is art 7, PE 8. We go to art 7 and we go up to PE 8. We put a cross, and we do that for all the points, and we get this scatter diagram. It doesn't matter if you put PE against art against PE, wouldn't make any difference. What we can see here is the points are all scattered about. There's no pattern to it. There seems to be no connection between PE score and art score. We say there's no correlation between PE and art scores. So that's a scatter diagram. There's nothing we can do with that. It's just showing PE scores against art scores. However, here's math scores against science scores. It's quite common for people who are good at science to be good at maths, and vice versa. So here it's maths plotted against science, and there's the scatter diagram, and this time these crosses seem to lie in a line with a positive gradient. The line seems to be going up to the right in a positive gradient. This means if you're good at science, you tend to be good at maths. Poor at science, you tend to be poor at maths. That's a positive correlation because they seem to lie in a line with a positive gradient. Here's a negative correlation. These points seem to lie in a line with a negative gradient, that is, the line's going down the way. This is saying that people who are good at science tend not to be good at PE. People who are good at PE tend not to be good at science. So that's a negative correlation. So a positive gradient here, a negative gradient here. So let's take the maths against the science. The points seem to lie in a line with a positive gradient. This line passes through the points, dividing the points roughly into 2 halves, those above the line and those below the line. 1 or 2 points lie nearly on the line, but there's no point bang on the line. So when we want the connection, the relationship between maths and science, we want to express it as an equation. We want the equation of this black line. We don't use any of the blue crosses because none of them lie in the line. We want 2 points are actually on the line as far apart as possible so that we can get an accurate gradient. So this point 1, 1 lies in the line, and this point 10, 6 lies in the line. So we want 2 points that lie clearly on the line and hopefully have whole number coordinates. 1, 1 and 10, 6 do. So if we work out the gradient of that line and use one of the 2 points, we can get the equation of the line. So here's the working for that. We want the equation of the line through these 2 points, get the gradient. So we get the y difference, 6 minus 1, and the x difference, 10 minus 1. The gradient is 5/9. Use y minus b equals mx minus a. That was in the third video. General equation of a straight line, gradient m through point AB. So 5/9 is the gradient. AB is just a point in the line. You could use either 10, 6 or 1, 1. I'll use 1, 1. So using 1, 1, A is 1, B is 1, and m is 5/9. Break the brackets. 5/9 times x, 5/9 times 1. And I'm going to replace this 1 by 9/9 because I want to sort out the fractions. So that's 9/9 is equivalent to 1. Add 9/9 to the left, add 9/9 to the right, and it tidies it up. And since it was maths against science, instead of having y and x, I've got m and s for maths and science. The equation of the line was m equals 5/9 s plus 4/9. S is a science mark, m is a maths mark, That is the equation of that line. That's the relationship between the maths and the science marks. Now, examples after this will be using simply y equals mx plus c, but we'll have the y-intercept. But it works in the same way. So here is a set of experimental results. The concentration of salt in solution is measured as a number of grams per litre, S grams per litre. The solubility depends on the temperature. In general, when you heat a solution up, more salt should dissolve. So the temperature in degrees Celsius is controlled. So you can control the temperature and then measure the solubility. So the solubility depends on the temperature. So we have a set of axes. We put solubility up the side and temperature along the bottom. Temperature's the variable we control. We can control the temperature. It's called the independent variable because you can choose what it should be. So we always put that along the bottom of a set of axes in science. So temperature goes along the bottom. It's the quantity we control. It's the independent variable, the one you can choose. Up the side is the dependent variable. The solubility depends on the temperature. So, temperature 5, solubility 9, we'd plot the point 59. Temperature 6, solubility 7, we'd plot the point 67, and so on. And we plot all the points, we get a scatter diagram. All these little crosses represent these points plotted. There are 25 points plotted there. They seem to lie in a line with a positive gradient. If we can get the equation of that line, we've got the relationship between solubility and temperature as a formula, and it would mean for any given temperature we can work out what the solubility should be once we get that equation. So, best fitting line is first, took all these temperatures, 25 of them, added them up and divided by 25. That's the mean temperature's 15. So the mean temperature is 15.2, but for the graph we can only go to 15. And added up all the solubility, all 25 of them there. So it worked out the mean of the solubility, it's 14.24, so that has to be 14. And we plot the point, temperature 15, solubility 14. There it is there, that blue dot. That's the mean temperature and mean solubility. And a line of best fit goes through that point. We try to put a line through that blue dot that roughly divides the crosses into half being above the line and half being below the line. Now, that line, as best I can get it, might be there. Now, it's a matter of judgment, so it might be that the line should have been a wee bit steeper or not. I actually arranged it so it would go through a nice clear point on the vertical axis. So, line of best fit takes a bit of judgment. Roughly half the crosses above and below the line, and it goes through this mean position. That's a line of best fit. The equation of that line gives the relationship between solubility and temperature, so that if you have a temperature, you can calculate the solubility using the formula. So we want 2 points on that line. We want them to be well spaced so we get minimise error. So it crosses here at 0, 4. It happens to be bang on 4, simply because I arranged it that way, but that's 0, 4. And there's another point up here, it's bang on 2420. So you've got to look along that red line and find positions where they're hitting on nice whole number coordinates, not fractions. So are as good as you can get with that in mind. So, and well spaced, because that way we minimise error. So we want the equation of the line through 0, 4 and 2420. At that point the statistics is over. It's simply equation of a straight line. Now, because we've got the y-intercept, we can just use y equals mx plus c. So there's that straight line. We'll use y equals mx plus c. You could use y minus b equals mx minus a. It'll work fine. So we get the gradient. And there's a gradient. Y difference, 20 minus that 4. X difference, 24 minus that 0. Fully simplify it, it's 2/3. C is where it hits the y-axis, 4 up. C is 4. Put that into the equation. Instead of saying y and x, it was s and t. So replace the y by an s and the x by a t. That's the formula. Solubility S, temperature T. Solubility was in the solution, the grams per litre, and the temperature was in degrees Celsius. So that's the formula that connects S and T. So if I had a temperature, like temperature 30 degrees, which is off the graph, 30 degrees, I would just put T to be 30. 2/3 of 30 is 20, plus 4 is 24, solubility is 24 grams per litre. So at temperature 30 degrees C, slipping that into the formula, you can work out S is 24 grams per litre. So that's the use of the formula. So it's an equation of the line, but it's a formula connecting S and T. So that's an example. So there's going to be a worksheet. If you click the link in the description, you can get the worksheet and it'll have the answers. This is an example of the type you'll meet in the worksheet. There's a graph W against N. There's a scatter diagram. Use dots here. And I want the formula connecting W and N. And then using the formula, you can work out W when N's 9. And using the formula, you can work out N when W is 7. So that's an example of what will be in the worksheet. So I want the line of best fit. That's what I reckon with the line of best fit. But again, if you judge it slightly differently, you've got a slightly different answer to what I'm about to show you. So there's a line of best fit as best I can see. It goes through here at 0, -3. And up here, that position, bang on the line is 11, 19. So once we get these 2 points from the graph, all we're doing is working out the gradient. 19 minus -3, 11 minus 0. That's a y difference over the x difference. It's exactly 2. Again, if your line was slightly different, you might end up with 2.1, 2.05, different things. Depends on what line you draw in. It goes through 0, -3, so C is -3. And you put that into y equals mx plus c. M's 2 and c is -3. And we replace the y and the x with the w and the n. And that's the formula, w equals 2n minus 3. So if you double n and subtract 3, you get w. There's 11, double it, 22 and take off 3 is 19. There's n0, double it and take off 3, you're at -3. So it works in these 2 points. Part B, using that equation, it said find w when n is 9, we just replace the n by 9. So replace the n by 9 and work out w. And then find n when w is 7, write the formula. Replace the w by 7 and solve that. Add 3 to each side, so 2n's 10 and then n's 5. Now, on the graph, if you look at where n is 9, there's n9, and if you looked up to the line and looked across, there would be the 15, which is what we got with the formula. There, we had w was 7, if you go to w being 7 and look across the line and look down, there's n coming out to be 5, what we got with the formula. So it works off the lines, but you'll be using the formula to work out the answer. Here's a second example. So it's P against R. Points lie on a line with a positive gradient. Once you get the formula, work out P and work out R using the formula. So what we do here is get the line of best fit. Now this red line, we simply want 2 well-spaced points. So that position there, 0, 4, and this position up here was on the red line, 24, 16. Now notice the points we picked, they aren't experimental points, they aren't any of the points which are the black dots. It's just got to be points on the red line, well spaced, and we want them on whole number coordinates. So well spaced but on whole numbered coordinates. So we could have used this point here, for example, 22, 15, because it's bang on a set of coordinates that are whole numbers. So gradient, y difference over x difference, 16 minus 4, 24 minus 0. Simplifies to 1/2. Meets the vertical axis at 0, 4. So c is 4. C is 4. Use that in y equals mx plus c. M's 1/2, c's 4, and instead of y and x it was p and r. That's the formula. So m's 1/2, c's 4, and instead of y and x it's p and r, whatever they happen to represent. That's the formula that relates the two quantities. It's the equation of the line. Now part B said work out p when r is 22, and part C said work out r when p is 10. So we had the equation of the line. P equal to 1/2 r plus 4. R is 22, put r to be 22. P works out at 15. If you were looking at the graph when r is 22, there's r22 up to the line, reads off at 15. And part C said find r when p is 10, so write the formula. Make p to be 10. Take 4 off each side, so 1/2 r is 6. And so r's twice that, double up both sides. R's 12. If you looked at the diagram when p is 10, looking at the graph when p is 10, there's 10. Look along to the red line and down. It reads off at r's 12, just what we got from the formula. So if you click the link in the description, you'll get these get the worksheet. I'll have the answers with it. That's what I reckon is a line of best fit for that first one, for example. So what I've done is I've put the worksheet on twice. First worksheet is so that you can do the line of best fit, but there's a second version which has the line of best fit on it. So it's just like in the examples, working out the formula and then using the formula in parts B and C. So each of them, a version with and without line of best fit, but it has the answers. So there's the worksheet as a PDF and 5 questions and the answers follow. And then same worksheet again, but this time with a line of best fit on it, followed by the answers. So you can have a version with and without the line of best fit, because the line of best fit will vary from person to person how you judge it, so you get slightly different answers if you do your own line best fit. There's a set of notes which covers all the straight line videos. So that was gradient from video 1 and some rearrangements of the equation in video 4. Y equals mx plus c and y minus b equals mx minus a, and that's the scatter diagrams, and that's a line of best fit. Hope you found the videos useful. Thank you.